Hi, this is Hyunsuk Yu, one of your TA, and today we will be going over question 3 in the 2012 midterm. Before I actually cover the question, I want to go over the general background related to this question. So we've learned in class that when you draw a molecular orbital diagram for a homoatomic molecule, you have to consider the atomic number of the element. So if the atomic number of that element is less than or equal to 7, we know that pi 2p is lower in energy than sigma 2pz. If the atomic number of the element is greater than 7, pi 2p becomes higher in energy than the sigma 2pz. For heteroatomic molecule, if both elements constituting the molecule it has a atomic number that is less than or equal to 7, pi 2p becomes lower in energy than sigma 2pz. On the other hand, if they both have nuclear charge that is greater than 7, then pi 2p becomes higher in energy than sigma 2pz. And if Z is greater than 7 for one atom and is not for the other, then there is no simple rule that can predict the energy level of pi 2p relative to sigma 2pz. So as I just told you, for boron, carbon, and nitrogen, the elements that have atomic number that is less than or equal to 7, we see that pi orbital have less energy compared to sigma 2pz. On the other hand, for oxygen and fluorine, the elements that have atomic number greater than 7, sigma has a lower energy than the pi 2p orbital. Now, there are some small things to remember when you draw the MO diagram. First, don't forget to label the y-axis and write down energy. Also, we have to write down the atomic orbitals that combine to give the molecular orbital. So it is important that you denote the heritage of the molecular orbital in your correlation diagram. Also, when you are drawing MO diagram for heteroatomic molecule, you have to remember that element that has a higher electronegativity has an atomic orbital that is lower in energy. Now, some possible questions that might come up in the molecular orbital diagram is first drawing the correlation diagram, and second, predicting the bond order. Third, predicting the bond length and comparing the bond length of different molecules. And also predicting whether the molecule will be paramagnetic and diamagnetic. And as you all remember, the molecule that have a lone pair electron is going to be paramagnetic, whereas if all electrons are paired, that molecule is likely to be diamagnetic. Now, let's go to question 3. Draw the energy correlation diagram for boron carbide, Bc. So since both boron and carbon have atomic number that is less than or equal to 7, pi 2p is going to be lower in energy than the sigma 2pz. And also, because carbon have greater electronegativity compared to boron, we can see that carbon have a lower atomic orbital energy. Now they combine to form a molecule, and you fill up the molecular orbital with the electrons. Now, what is the bond order of Bc? We know that bond order is 1/2 of bonding orbital electron minus anti-bonding electron. So in the diagram, we see that there are 5 bonding electrons, whereas there are 2 anti-bonding electrons in the sigma 2s star. So the bond order is half of 5 minus 2, so the bond order will be 3/2. Now, rank BC, BC minus, and BC plus in the order of bond length. We know that the highest occupied molecular orbital for boron carbide is pi 2p, which is a bonding orbital, and there are that orbital can accept one more electron. So boron carbide will have the highest bond order, whereas Bc plus will have the lowest bond order. And since the bond length is inversely proportional to the bond order, we can see that Bc plus have the largest bond length, whereas Bc minus have the smallest bond length. And that was the end of question 3, and everyone good luck with the exam. Thank you.